temperature. I could, but I didn't. And I would have had to have given you the rest of this. Maybe I did it in a snarky way by, who knows, but I've given you all the parameters except one because you only have one equation, there can only be one unknown. Again, look out for me being snarky about it, but understand, unless I made a major mistake on the test, which I hopefully have not done, I have given you all the parameters except one. So if you feel that I haven't, I have. Just take it easy and look more closely, or go away and come back to it later. Okay, now delta H, delta U, plus delta PV still. And as usual, I've already got this defined. NR delta T. And therefore I've got CV plus NR delta T, which is CP. And of course I'll give you CP. But remember, sometimes CP is not equal to CV plus NR. Sometimes it's not perfect because of gas imperfections, right? Joule-Thomson, that kind of stuff, which is not on the test. That was on last test. I often will give you CP, and it will be very close to that, but it's not always exactly right. And I want to give you real numbers. And remember, it's not always perfectly correct that these are equal because of imperfections of real gases. Okay. It's delta S, right? Okay, let me be careful. No, wait. Let's do it this way. Just trying to think of the simplest route, because there are multiple routes. I want to do the simplest one. Change over temperature. Reversible, be minus, right? Because what happens inside is the same as outside, but it's all zero. Okay, yeah, adiabatic, these are zero. Maybe that's one of those things I can write down. I can't write that down initially in this case. Okay, so therefore, which is zero, changes S of the surroundings, which is zero, change in S of the system, therefore, change in S is also zero. Okay, change in S of the system, surroundings, and total, delta S's are done. Now remember that you can do this. And I had you do this before on the homework. VF over VI. Wrong. I screwed myself. Just had to take that off the test. NRLN VF. And remember, the damnedest thing is this still works. It's just that in your homework, in case you forgot, you plugged in this relationship. Like the VF and the VI, you plug that into here in very simple manipulations. This does turn out to be zero. And I even had you work it on a question, which case, there's rounding errors. You found that it was a very, very small number because of rounding errors. It really is zero. Okay, S's. Okay, now A. Okay, now A is U minus TS, so the change in A is the change in U minus the change in TS. And I'm writing it like this because this is always difficult. A's and G's, I know I'm not going to find an answer. So I'm not going to integrate it in my head first. I'm going to start lower level and then integrate it later to delta A. Okay, changing U is CVT. Yeah, I'm just being extra cautious. Minus TVS minus SVT. Okay, we do have a saving grace in that's zero. Okay, CV, DT, minus SVT. Now the damnedest thing is, to get to the real delta A, you have to integrate it. Not a problem, CV, delta T. We'll ignore temperature dependence on CV, but that's not a big deal. Right? Remember that heat capacities are temperature dependent. And we did have a little fancy equation for that. S, you don't want to do that. Problem. The problem is S is temperature dependent. So just like before, when I had PdV, I couldn't ignore the volume dependence of pressure. It was important. It has to come out. It changes the answer in a big way. S is a strong function of temperature. It changes a lot with temperature. So while I would like to just bring it out and say it's SDT, and S will be the number in the table at the back of the book, you're going to get pretty far off without going too far of a change in temperature. And so notice that I have S is equal to T, but S is kb, natural log of the number of microstates, which I usually express as W, but the number of accessible microstates is a function of temperature. What's the equation for that? I don't know. That gets real hard. That's why graduate students go to grad school. If you actually want to answer this, you need to go to grad school because this is the way you're going to have to do it. And we work example problems where real chemical problems like electrons and metals, you can do some things like that. And we teach the graduate students electrons and metals, perfect gases. You can determine these and you can see their temperature dependence and then you can actually integrate it. But that's just not appropriate for this class. You could actually, if any of you took 444, you could actually do this. You get into a little bit of it, and it's not really very hard. 444, by the way, that's PChem 3. It's actually almost not mathematical. It mostly involves group theory and spectroscopy, which actually you can do all that without doing any, without doing integrals. It's actually a symmetry class. It's actually much easier than this class, in all honesty. It's definitely going to be easier than 346. So in this case, now, let's relate that to knights on a chessboard. What if some of those squares are higher than others, and it takes heat to jump onto them? You see, that's what I mean. If it's cold, the knight can't jump onto that higher ground, but if the knight has some kick in the pants from heat, it can. And that's why the entropy changes. It has more squares if it gets hotter, but that becomes very difficult to figure out. The way I would actually do this, since S changes with T, so I can't, what I'm really trying to get at is that there is no analytical solution, or not an easy analytical solution at the very minimum. And analytical means e to the ln vf over vi times sine of cats, right? Now there's a numerical solution. So what I would do is I would calculate S as a function of t, which rises like a natural log, for reasons we've gone over, especially the inverse equation. So what I would do is I would calculate, for every degree, what S was using where the hell it went. Oh, where did my entropy go? Oh, yeah, here. So I could do this. I would just discretize temperature. See, here's the problem. Ti over Tf. I need a function. This isn't really a function. This comes in jumps. So what I would do is I would say, if I'm going from 25 to 100, I would just divide up T into 1 degree increments, calculate S, and because I'm going to integrate as a function of T, you remember Simpson's rule? Right, I would do it like this. I would divide up space into little increments, and these become little rectangles, and then I add up the areas, and anyway, I don't even know why I'm still doing it. And so then this area ends up being T delta S. That's how you have to do it. You have to use a computer. That's why I never asked you to do it. So it is doable, but it's done numerically, not by pen and paper, right? Computer, pen and paper can't be done on pen and paper, needs to be done on a computer. Okay, delta G is delta H, which is delta H minus delta TS, which is going to be the same. It's going to be Cp dt minus TdS, which is 0, minus SdT. Same problem. There's just no good way to do this. So I don't ask this on adiabated questions. I don't ask for A and G, because you can't. Is that all of them? Did I do it right? Okay. Holy God, I've really let the time go. Sorry. Our last one is actually kind of easy. Adiabated irreversible. And then I want to tell you a little bit about the test. A little bit more, just tell you how the grades will break down. Okay, adiabated irreversible. Okay, like before, this is going to be kind of easy because a lot of them are the same. All right, again, there's no point in doing this again because of use. That thing still works. because U is path independent. So there's no point in doing this. Sorry, I should have a delta t. Now again, I need to get to delta t, and because this is also the change in work, because the change in heat. So as soon as I get temperature, I get U and W, and so that's good. I'm going to get to some others. But now the hard part, although remember that this seemed easier. You solve, from here you solve for T final. I mean, I can set this up other ways, but that's the way I would choose to do it. You set that up to find T final, and you do that by making V a function of T. So otherwise, see, you have two unknowns in one equation. That is unsolvable. But because V hides T, has T initial and T final in it, you just convert the V's into T's, and then you have an equation with everything given to you except the final temperature. One equation, one unknown, it's solvable. But you recall, that sucked. Right? This guy ended up being infinitely easier than this guy, even though it looks infinitely worse. This looks simple, but it's not because of that conversion. So I won't say anything more about that. But you get T final, and there you go. I got U and W, and I got Q. I don't care if you put deltas or little d's, it doesn't matter to me. Delta H is still going to be, it's going to be the same. I'm not going to go through it all again. It's going to be Cp delta T. Okay, and okay, UHWQ. So now I'm on S, right? Sorry, not working the board too well. Let me just go over here. I'm almost done. Okay, and this one is another real pain. Change of S. We can change in Q. So remember last time I had a cutesy little way of doing this because the total was 0 and the surroundings was 0. Oh, and let's actually, all right. Sorry, I'm being an idiot. Surroundings will be 0. Sorry, that's one of the ones I can do instantly. Again, because I'm adiabatic. All right, but in this case, the change in total is not 0 because I'm not reversible. Does that mean my snarky way of getting this to be 0 for reversible? I don't have access to that. So I'm going to have to do something like this. So let's see if I expand, temperature goes down, and there's a certain change in S. But S is a state function and can be path independent. Okay, change in S1. An isothermal expansion, that's what's happening. So that's NR, just like before, and I'm not going to do it. Isothermal, I've already done it. NRVF over VI. For the same reasons that when I did an isothermal expansion. Okay, then the second part, which I'm going to add together. Again, change the T. Okay, now this is This is not isothermal. It's a heat change at constant volume. Okay, if I'm at constant volume, and this is the change in U over T, which is CV dt over T. And then I integrate it. Oh, sorry, this is integrated, right? Sorry, I do try to be careful about this. Because you guys get on the case about it, which is fine because I'm not doing it right. Okay, so that means that delta S total is the change in S of the system. I've already defined this as 0. And it's NR LN DI ln T over Ti, so the sum of the two legs. And if you've done it right, it is greater than 0 joules per Kelvin. If you've done this, if you did this part right to get TF, this will be greater than 0. It has to be. And it's just crazy how that just happens to work, but you can't get a negative system change. Otherwise, it gets all screwed up. Okay, real quick, I want to spend at least a minute on the test. Change in A is a change in U, minus a change in TS. And that's CV dt, which is not hard, minus TDS, minus SDT. Okay, I already told you I can't figure that out. It's worse now. T isn't constant. If S is a function of T, T is a function of S. And it's changing, I already know it's changing. This is, I have no idea how to get to this guy. And I already couldn't do that one. Got stuck. So, it's not X. Again, I'm sure there's a computational way to do this. And remember, dg is just cp, dt. That's the delta H. TDS. And remember, one reason is that there's no PV equals nRT for T's and S's. Because of S's, KL and W, because of that, it's complicated. There's no good perfect gas law with S's and T's in it. Did I do it?
Yeah.
Ha! Oh, stuck it. All right. Well, I hope you had fun. I did. That's more important than anything. Okay, real quick. Let me give a shakedown. Sorry, I spent way too long on this. I didn't think it would take so long. Probably because I ran out at the beginning about a bunch of bullshit. Okay, so what did I start with? Like derivations. Do you want to see this on the test? Huh? Like a constant t. I have S. Okay, so I warned you that what I could do is I may give you a relationship like this and then say, hey, what's the change in S? So this is an example of what I could give. The question I have on the test is very similar. It's not exactly this. I need you to bring this over and recognize that P has, so I already did this. And then you integrate it. And that's MR ln. Okay, so look for something like that. So the types of derivations. I also do have one quick question like this. Okay, so real quick, 100 people that live in one city. What's S?
0.
What's W? 1. Right, there's only one city. There's only one way 100 people live in one city, right? So, now you see how I'm throwing you off? I'm throwing a big number at you, but it doesn't matter. It only matters the number of places those 100 people live. There's only one place, so that's 0. One person in 100 cities.
ln 100.
ln of 100, KB ln of 100. 100 people, 100 cities. Oh, that's a permutation. That's like a big number. Anyway, okay, so there's that. It's easy. I made it easy. It's just like that. But remember this stuff. So that's minus PdV. That's work heat. And so change in A is minus PdV. Remember your Maxwell relationships. By the way, in derivations, you need a Maxwell relationship. I gave it to you. Also, the Maxwell relationships are on the cheat sheet. Again, that's why I want you to be aware of that. And I hate cheats. Remember, this is the Euler relationship. dP, dt, the P dt, a constant B, is changed to S because the negatives cancel. The S can be a constant T. So you may run into this. So you go there because this can be solved with PV equals nRT. And on those derivations where you do that, they'll all be for perfect gases. Speaking of which, all right, another type of derivation you have had, and you don't want to ask, is the usual, this is on there, the usual, for example, the H, the V, and I'm not saying this is what's on there, 0 for perfect gas, but it's not 0 if P is all right, so I've got one of those on there. And just look at the example. Do the problem you've already did. Just make sure you can do it. Because you know what I did? I made it easier. I asked a question like under homework. I made it slightly easier by changing the van der Waals equation to make it easier. So do that question, answer it right. You will have no problem with the question I ask on the test. Okay, open systems. Like remember, if this is true, what condition do I have? Right, equilibrium. If the chemical potential of A is greater than the chemical potential of B, What's happening?
Spontaneous reaction.
A reaction, but which way?
Product.
A goes to B, right. Energy flows downhill, so don't forget that. This is on the test in a snarky way. I think that's a true and false. Just go ahead and tell you that. Okay, now I did tell you, and this is true, that I did have Henry's Law and Reynolds Law. I wrote a handout, by the way, just in case, but I made a slight error. I made the solute B and the solvent A, and I did it the opposite in class. Sorry, it's kind of too late to fix it now. I don't have the time. I got to write a grant, fortunately. So remember that mixing G is delta mix H minus T. Again, we live in a constant temperature world. And again, I missed that minus sign on the nose, that was stupid. Where delta mix H is the change in mix, I hate writing that, plus the change, we're in a constant pressure world, so the P comes out. And then if it's ideal, these are all 0 joules, and therefore delta mix G is minus T delta mix S. Now then we borrowed our concept of how does entropy change for vapors, which are gases, so we inserted our vapor thing, and then we just said, well, if I divide delta G mix by 1 mole, it becomes a chemical potential, and it doesn't change, right? So that's a snarky little trick, and therefore, for ideal solutions, again, this is ideal, PA over PA naught is just going to be mole fraction of A by Dalton's law. So delta mix, sorry guys, I'm almost done. I'm sorry I held you over. nRT, mole fraction of A, natural log mole fraction of A. Okay, remember that this is NART ln of the pressure change of PF over PI, and which I'm approximating as the mole fraction. You can't forget that there's 2 things present because you mix 2 things. Okay, again, this is ideal. Now, if you have ideal dilute, you can say that delta H, which is approximated as B chi A chi B, nRT. If you have that, sorry, I'm in a rush. If you have that, you can say then that delta mix G is nRT, and again, I'll make the A the solvent, the solute. What you have is the Henry's law constant. Okay, so that's Henry's law, but for solvents, Reynolds law is followed. Yeah, I'm sorry about this. Okay, now if you're not ideal or ideal dilute, so I'll call this the neither. And you have activities, and that's nRT. Remember that this is kind of a crappy cheat. ln activity of A plus chi B ln activity. Activity of B. Where activity, again, this is on the test, is defined as gamma mole fraction, which just makes everything work. And we also saw that in the limit, using this guy here, in the limit of chi A going to 0, or chi B, solvent going to 1, you return ideal dilute. You return ideal dilute solution. So my advice on the test, don't ignore this. Look at the notes. Hint, hint. It's on the test. That's the hint. You see one of the questions. Oh, I'm sorry. You got it now, right? Huh? Huh? I'm way over. You got. I held you 5 minutes too long. I'm sorry about that. You done? Okay, ask me questions afterwards, because I know you went too long. Sorry about that.